Hello everyone. So today we're starting the second chapter of this first part on the Dimer model. The title is Dimer Configurations on Surface Graphs. So we've been talking about perfect matchings for a while, but actually perfect matchings are also called Dimer configurations. Or Dimer coverings. So people in combinatorics talk about perfect matchings. People in chemistry, statistical, physics talk about Dimer configurations. And Dimer, you should understand Dimer, the word Dimer as like polymer, monomer. You know, polymer is molecule with many atoms. Dimer, something which would look like this. And as I said in the introduction, you can, if you have a weighted graph, so G, a graph, so let's say G nu, a weighted graph, you can wonder about the computation, so you can define the partition function for the Dimer model on the weighted graph G nu, which will be a sum over all Dimer configurations, or perfect matchings of the graph, and with this. So is the partition function of the Dimer model on this graph. And the question I had asked already like 3 weeks, 4 weeks ago, 2 weeks ago in the introduction was, can you compute this efficiently? And of course, we already know that the answer is no in general, because even if you look at biparallel graphs and even if you put all the weights equal to 1, you're already not able to compute this because this is the number of perfect matchings, right? So by Valiant theorem, which we saw last time, the answer is no in general, even for unweighted bipartite graph. But today, of course, we're going to see a positive result, which is basically that actually if the graph is planar, then you can do it. Okay. Today, one of the nicest theorem of the class, I think. Basically, the answer is yes if the graph is planar. That's what we're going to prove. And of course, now you see the word plane, the word surface, and you begin to understand that there are other tools that are going to come into play. And so before going into this, I will stay on abstract graphs for a while. It's the first paragraph of this chapter, Dimers and Pfaffians. Okay, so we need to do a little bit of linear algebra first. Let A be a skew symmetric matrix. I will introduce or recall what is the Pfaffian of a skew symmetric matrix. You might know already what this is. So the Pfaffian of A is defined as, so 1 over 2 power n factorial, sum over all permutation of 2n objects, the signature of the permutation, which, remember my convention, is plus or minus 1, and then A sigma 1, sigma 2, A sigma 3, sigma 4, A sigma 2n minus 1, sigma 2n. This is the definition of the Pfaffian if A has size 2n, so even size, and the Pfaffian of A is 0 else, if A has odd size. Recall that if a skew symmetric matrix has odd size, its determinant is 0. So we also said Pfaffian equals 0 in this case. Okay, so I'm going to give you, so just maybe just one example, one stupid example. And then I'm going to give you several properties of Pfaffians. So if A is 0A minus A0, that's the general form of a 2 by 2 skew symmetric matrix, then what do we get as a Pfaffian? So n equal 1, we have 1/2. And then here, so we have the identity, which gives you 1, 2, that is A here. So we have A plus minus 1 for the signature times minus A 2, 1. Okay, so that's permutation identity, permutation given by the transposition. We have minus A. So here we get A. So let me give you maybe 5 or 6 properties of the Pfaffian. The first property, which I will actually not really use, I think. So I'm not proving it, and I will not even give it in homework, but it's an important property, is that actually the Pfaffian is a square root of the determinant. So now you understand why we set Pfaffian equal to 0 if A has odd size, so then this is trivial. So basically what really the Pfaffian means is if you have a skew symmetric matrix of even size, then its determinant is the square of a polynomial in the coefficients, and this polynomial is given by the Pfaffian. Okay, so the Pfaffian is a choice of a square root of the determinant of a skew symmetric matrix. Okay? Second property, maybe the most important one. So, okay, so it doesn't make sense. So we'll try to mimic some properties of the determinant. It doesn't make sense to say the Pfaffian of a product is the product of Pfaffian, right? Because if you take two skew-symmetric matrices, their product will not be skew-symmetric in general, so it doesn't make sense. But if you take a skew-symmetric matrix and then a square matrix of the same size, and you look at this, then this is indeed also skew-symmetric. So it makes sense to consider this, and the Pfaffian of this is equal to the determinant of B times the Pfaffian of A. And this is for any A skew-symmetric and for any B of the same size. Okay. I will comment on. So this property is extremely important. I will comment on it later on. For now, I'm just going to list the properties. So third property, the Pfaffian of a direct sum is the product of the Pfaffians. Okay, for any A prime skew-symmetric, of course. 4. There is a special class of skew-symmetric matrices which is quite interesting, is the ones that are, well, that will occur naturally in our study. So ones that have this, that are of size 2n with of this form. Right? So this is, of course, skew-symmetric, and here you have size n and n. And so this is related to the determinant of k. There's just a sign coming up. And the sign is given as follows. It's here times the determinant of k. Okay. Two more properties. Number 5, if you have, so for any ordered subset I1, J1, IK, JK of the ordered set 1, 2 to n, we have, so I want to consider the derivative of the Pfaffian. So this is a polynomial in the coefficients A, I, J. And I want to differentiate the Pfaffian with respect to k of these coefficients. And so there is a formula for this. This is the signature of some permutation, which I will write down in 1 second, times the Pfaffian of A. So let me explain this. Where so I is this subset. A, I, C is for complement denotes A with all rows and columns corresponding to I removed. Okay, so you take A, and each time you have a row or a column whose index is in I, then you remove it. Okay, and finally, what is this permutation here? Sigma I is the permutation of 1 to 2n, which sends, so this ordered set 1 to 2n. Sorry, I'm still going to write it here. I send all of this first to I, and then to 1 to n minus I. I hope this is readable and understandable. So it means you first take I1, J1, I2, J2, IK, JK, and then you put all the others in with their respective ordering. Okay. So I hope all of this is clear. And I'm just going to give you one last property. Of course, now they come up in a, you wonder why they come up, but obviously you know that we're going to use them soon. So I want one last property, is that if the Pfaffian of A is non-zero, then A is invertible. This is obvious because we know it's related to the determinant. And in this case, I can rewrite the right-hand side here complement as Pfaffian of A times Pfaffian of A inverse I. And so now this should be clear from the notations before. It means you take so A is invertible, so it makes sense to consider A inverse. And then you look at all the rows and columns of A inverse whose indices are in I. Okay, so this matrix is of size 2k. This matrix here was of size 2n minus 2k. Okay. And there is a sign which I forgot. So let me just write this sign. Minus 1 to the power k. Okay, so let me comment on these properties. First of all, so property 1 is not very difficult. Well, it's okay. I'm not going to prove it, as I said. Properties 2, 3, 4 are in homework. So properties 2, 3, and 4, this is homework of this week, exercise 1. 5 and 6 we're not going to prove. So let me make a remark. So obviously you understand what we're going to do with the Pfaffian. We're going to try to use it to compute this partition function. And we saw that, I mean, we had already a polynomial that was working completely fine. It was the permanent, right? But the permanent was not computable. And now what we're gaining with the Pfaffian is that actually, well, the property 2 here actually tells you almost immediately that Pfaffian is computable. Because this means that you can actually play with rows and columns. You can make rows and columns operations exactly like you do for the determinant. And so you have kind of a Gauss algorithm to compute the Pfaffian exactly like you do for determinants. So property 2 implies that there is a, let's say, Pfaffian calculus indeed, one can use rows and columns operations, row and column operations, to transform any skew symmetric matrix A into matrix A prime of the form. So it's not a diagonal matrix this time, of course. Otherwise, I mean, diagonal skew symmetric matrix is not very interesting. But it's a matrix of the form, so 0, A1 minus A1, 0, 0, an minus an, 0. And the Pfaffian of such a matrix by property 3 And the example we had worked out, the Pfaffian of this is A1 times A2 times AN. Okay. So, sorry, so transform, excuse me, into this without changing its Pfaffian. Without changing Pfaffian, so Pfaffian of A is equal to Pfaffian of A prime, which is equal to the product of these coefficients by property 3. And the small stupid example we had worked out before of a 2 by 2 matrix. And actually this can be done in we go over cube operations.
A question about part 5. I missed this sigma subscript I. What is that?
Yeah, so it's here. So it's the permutation that maps the ordered set 1, 2, etc. until 2n to the ordered set where you take I1, J1, I2, J2, IK, JK, and then you look at all of these without the ones you already taken. Okay? So that's a well-defined permutation of 2n objects, so you have a signature, and that's it. Okay. Any questions about this, about the Pfaffian? Good. So now we have a new candidate to try to compute matchings. Maybe just a remark so you understand why this case is interesting, because if you take, so of course now we're gonna take a Pfaffian of a adjacency matrix for a graph, and you see that if the graph is bipartite, then the adjacency matrix has this form, and therefore you will have that, and the K is exactly what we call, well, will be what we had called the bi-adjacency matrix, and so we're gonna, okay. Okay, good. So how does this relate to matchings? Does Pfaffian relate to matchings? So before going back to graphs, I need just to make one comment on the Pfaffian, one last comment. Okay, first, note that any permutation of 2n objects determines a partition, I'm not going to say a matching, a partition of the set 2n into n unordered pairs, sigma 1 with sigma 2, etc., sigma 2n minus 1 with sigma 2n. So let's say, I'll say a partition P. That's right. Furthermore, the monomial I'm going to write it A sigma. It will be the contribution of sigma to the Pfaffian. So remember that was the signature of sigma times A sigma 1, sigma 2, A sigma 2n minus 1, sigma 2n. I claim that this monomial only depends on the partition P induced by sigma. So do you understand this? I'm saying that any permutation determines a partition of this set into n unordered pairs. Furthermore, the contribution of the permutation to the Pfaffian, which are denoted by A sigma, only depends on the partition. Why is that? Well, if you have another permutation which gives the same partition, it can be obtained from, it is related to sigma by two kind of moves. Either you change the order of pairs, and in this case you have an even signature. Well, you have +1 signature, so you have an even permutation, and this will not change, right? So this doesn't change, and this doesn't change. Or you change the order in one of the pairs, but in this case you have the signature that changes sign, and since the matrix is Q-symmetric, you will get a minus sign here as well, right? So in both cases, you see that this thing here does not change, right? So maybe I'm going to write a few words with what I just said. Indeed, if P of sigma is equal to P of sigma prime, then sigma and sigma prime are related by finite, well, by the following moves. First move, permute the pairs. The pairs, and so in this case we have signature of sigma is equal to signature of sigma prime, and nothing changes. We put it this way. Second, permute two elements inside a one pair. And in this case, the signature of one is equal to minus the signature of the other. But since the matrix is Q-symmetric, it works. Since A is Q-symmetric. The conclusion is that actually the Pfaffian can be defined in a kind of simpler way. It's just a little bit more annoying to write. It's simpler to compute, it's more annoying to write. The Pfaffian is actually, sorry, and one more thing. How many permutations will give you the same partition? Well, you have 2 to the power n for these, and then you have n factorial for the order of the pairs. So it's exactly this 2 to the power n times n factorial that was in front, that was in the denominator of the Pfaffian. So furthermore, there are 2 to the power n times n factorial permutations for each partition. And now I can write my conclusion. The Pfaffian of a matrix is really equal to the sum over all such partitions of AP, where AP is equal to A sigma for any sigma representing P. Okay? So it's simpler because you have much fewer terms to compute, but it's more, notationally, it's a little bit more annoying. Examples. So let's try again the stupid example we had, 2 by 2 matrix. So we have to sum over matchings of 1 and 2 in two pairs, so you have a single one, of course. You can only match 1 with 2. And, well, you get immediately that this is equal to A. Okay. And now we can also look at a general 4x4 matrix, A, B, C, D, E, F. Okay, so how many matchings do I have? I have 1, 2, 3, 4. I have 1, 3, 2, 4. I have 1, 4, 2, 3. And these two give a plus sign. This one gives a minus sign. And so now I have to take A, 1, 2. That's A. Then A, 3, 4. That's F. Then 1, 3, C, 2, 4, E, plus 1, 4, sorry, it was a mistake, it's the B, plus 1, 4, C, 2, 3, D. I think that's correct. Let me double check. A, F, B, C, D. Yeah. Okay. Now let's go back to the problem we have in mind. So let G be a graph. And since we want to compute the number of perfect matchings, or we want to compute the partition function for the Dimer model, we will assume that G has an even number of vertices. Otherwise, there is nothing to say. With an even number of vertices, and let's number them. So let's say VG is 1, 2, till 2n. And I'm going to take a weighted graph. Okay. Okay, now what I want to do is to associate to this weighted graph a skew-symmetric adjacency matrix. So if I want this matrix to be skew-symmetric, I need to add something on the graph, and this will be an orientation on the edges. So let omega be an arbitrary, so for some time it's going to be totally arbitrary, orientation of the edges of G. To this, now we're going to associate a weighted skew-symmetric adjacency matrix for the graph. Okay? So to this, let us associate a, so it's really the weighted skew-symmetric adjacency matrix. So I'm going to write it as A omega. It really depends on omega, but also, of course, the weighted graph. And I will denote its coefficients by Aij omega like this. And you understand, I guess you guess what are the coefficients. So Aij omega is defined as follows. So first case, you put plus the weight of the edge E if I and j, so now these indices correspond to vertices, if the vertices I and j are linked by an edge E which is oriented by omega from I to j. Then you set minus nu of E if you have the same story but with the orientation going the other way. And you set 0 if I and j are not adjacent. Okay? And so this, I will denote all of this by epsilon omega ij times nu. What did I want to take as notation here? Yeah, okay. Nu of E. So this is simply a notation for this sign here, plus or minus. And okay, so this is if the graph is simple. If the graph is not simple, you just sum over all edges, okay, with the same things. So this is if G is simple, else sum over edges. So I'm not going to do this, but it works completely fine in the complete general case. So you agree that this matrix is skew symmetric, right? Really by definition. So by definition, A omega is skew symmetric. So let's compute its Pfaffian. Okay. Pfaffian of A omega is equal to what? So it's the sum over all P partitions. So I'm going to write it this way. So P, a partition of 1 to 2n into pairs. Pairs sigma 1, sigma 2, sigma 2n minus 1, sigma 2n. And here I have, so remember it, sine of sigma, A omega, sigma 1, sigma 2, A omega, sigma 2n minus 1, sigma 2n. And now this was a trick we had already seen with the bi-adjacency matrix. You see that what's going on is here, if the partition is not supported by a perfect matching on the graph, then this term is 0. So here what we're doing is we're actually summing over all the perfect matchings of the graph. And what is the corresponding coefficient for a perfect matching? Well, you see, it's going to be the product of the edges in the perfect matching, so this is very nice. It's exactly what we want. And here, we'll have a sign, which I will denote by epsilon omega of m. It's a sign which depends on m and on omega, on the orientation we fixed, where epsilon omega of m is equal to the signature of sigma times epsilon omega sigma 1 sigma 2, etc. Epsilon omega sigma 2n minus 1 sigma 2n, if sigma is a permutation which represents m, is any where sigma is any permutation representing m. Okay? Good. So now the goal is, so this works for any orientation omega. So it means that now the only thing we're left with is to find an omega such that this sign will not depend on n. Right? If we find this, then we can factor out the sign, and we're done. And then the Pfaffian is equal to the partition function, and we're done. We're happy. We can compute the partition function in, as a Pfaffian, that is, in polynomial time. Goal: find an orientation omega on G such that epsilon omega of m is equal to epsilon omega of m prime for any m prime perfect matchings on G. Why? Because this would imply that the Pfaffian of A omega is equal to a plus or minus the partition function. And since this is a positive number, we will have that the partition function is simply equal to the absolute value of the Pfaffian. And then we're happy. You all agree with this argument? Okay. So now here comes a lemma, and maybe I will try to prove it before the break. Maybe I'm going to finish slightly late the first hour, but I think now, I really should go on until here. Okay, so now the point is, if you have an orientation omega, two perfect matchings m and m prime, you want to understand the product of these two signs. And you want this to be +1. Okay. So let's try to understand this. Given n, m, m prime, two perfect matchings, consider the symmetric difference. That's a trick we use so many times already. And we know this is a disjoint union of even cycles. So even cycles, disjoint. Right? We had seen this already at the very first class, I think, with Tute's theorem. Set n omega of C to be equal to what? I want to look at the number of edges in C oriented backwards by omega when running along C. So what do I mean by this? I have a cycle, and I have an orientation on each edge of the cycle. I pick any orientation of the cycle, I go along it, and I look at the number of times the edge faces me. And of course, in general, this is not well defined, but actually, here we have cycles of even length, and if you take a cycle of even length, then the parity of this number will not depend on the choice of the orientation you have. Okay? So since C is even, the parity of n omega of C is well defined. So does not depend on the choice of the orientation of C on the way, let's say, the way we run along C. And the claim, so now the claim of the lemma, then the product of the two signs is equal to minus 1 to the power sum over I n omega ci plus 1. Is the statement clear? Okay, so maybe I'm not going to give the proof now, but just going to say, so hence, we have so I had a goal here, now it's going to be a goal prime. Remember, we want this to be equal to this. This means we want this product to be equal to 1. This means we want this to be even. This means we want this to be odd all the time. So it means that what we really want is to find an orientation omega, goal prime, find an orientation omega such that for any cycle C of even length, that can be realized as a composition cycle of two perfect matchings, right? That can appear as a composition cycle of two perfect matchings. And what is this? So it takes a little while, but if you think about it, it's clear. A cycle can appear as a CI here if and only if, when you remove it, the graph you have admits a perfect matching. So I'm going to write this. For any cycle C of even length such that the graph I get by removing cycle admits a perfect matching, what do we have? N omega of C is odd. You agree? So, in parentheses, these C's are exactly the cycles that can appear as composition cycles, or so can appear in a symmetric difference. And this leads to a terminology an orientation omega as in this is called a Pfaffian orientation. And a graph is called Pfaffian if it admits a Pfaffian orientation. And all the discussion we had until here, module the proof of the lemma, which I still need to give you, says that if omega is a Pfaffian orientation, then the Pfaffian gives you the Partian function, right? So if you have omega, which is Pfaffian, then the absolute value of the Pfaffian of the corresponding skew symmetric adjacency matrix gives you exactly the Partian function. Okay? So of course we know that at some point it's going to break down because we know that you cannot always compute this. We know that not every graph is going to be Pfaffian, right? but at least now we have a better understanding of what we need to find. So, okay, let's make a 10 minutes break. Okay, I start again at 15 past. I'm going to give you the proof of the lemma and then show you that every planar graph is Pfaffian. Okay, so let me give you the proof of this lemma. I think it's a really nice proof. So we fix M prime to perfect matchings, and we consider their symmetric difference, which we know is given by a disjoint union of cycles. Okay. So maybe I'm just gonna that would be M, and then we have the edges of the other perfect matching, say M prime. Can you see the difference? It's okay. Okay. And now remember, for the expression of these signs, we can pick up any permutation which is representing M and M prime. So now we're going to make a smart choice. So let's orient the CIs arbitrarily. So number and orient the CIs arbitrarily. And consider sigma prime representing M and M prime as illustrated opposite. So I'm going to give you, let's say that this cycle here is the first one. And then let's say that we orient it this way. And okay, I also have to pick up a first point. So I'm going to say that this point is sigma of 1. This point is sigma of 2. And then I'll say that this is sigma 3. This is sigma 4, etc., etc. Okay? And then I do the same for, I continue with another cycle where I pick an orientation, I pick a first point, and I continue. Sigma to m plus 1, sigma to m2, etc. And this obviously is indeed a permutation which represents my matching, right? It works. Sigma 1, sigma 2 is a dimer of M, sigma 3 is 4, etc. And then I will pick this one as sigma prime 1. This one will be sigma prime 2. This one will be sigma prime 3. This one will be sigma prime 4, etc. You get the trick? You agree that sigma represents M, sigma prime represents M prime. We had a huge freedom for how to choose them, and we choose them in such a way. Okay? It's not unique. It's determined by a numbering, an orientation, and a first base point for each cycle. Okay. Now let's see. Note that so if I look at sigma prime composed with sigma inverse, what is this? Sigma prime composed with sigma inverse. So I start with this vertex here. I make sigma inverse. So I go to 1. And then I put sigma prime. I arrive here. So this vertex here will be sent here. Now if I continue, sigma 2. So sigma inverse, I go to 2. And then sigma prime, I go here. So you see that this permutation is actually permuting each cycle by one edge in the orientation we have chosen first. Okay? So is a cyclic, well, is a permutation of each cycle by one edge. But this means that the signature of this permutation, so this implies that the signature of this permutation is what? Is -1 to the number. Well, when you have, so these cycles, they represent a decomposition of this permutation into disjoint cycles, right? So it means that if you want to compute their signature, this is product. So this is -1 to the power of the sum over all cycles, the length of Ci plus 1, right? The signature of a cycle of length L is -1 to the power L plus 1. But here, remember that Ci is always even. So Ci is always even. So it means that this is -1 to the power the number of cycles. Okay? So now, using sigma and sigma prime, we now compute. I want to compute the product of these two signs. First, I put the two signatures. And then I order the remaining signs that come up exactly as here. So it would be sigma 1, sigma 2, epsilon omega, sigma prime 1. I don't read well here. Sigma prime 1, sigma prime 2. Omega, sigma 3, sigma 4, etc. Well, this now, we just saw, this is the same as the signature of this, and we just saw it's -1 to the power of the number of cycles. And now by definition, if you look at this, what is this? This sign each time is +1 if we go in the right direction, -1 if it's facing us. So this thing here is exactly -1 power sum and omega of Ci. Right? That's just the definition. So we get exactly what we want. Everybody okay with this? Okay, so now I go back to the discussion we had. We try to find an orientation omega such that each time you have a cycle of even length, such that when you remove it, you still have a perfect matching. This cycle has n omega odd. And if this works, it's fine. And if you can find such an orientation omega, you say that it's a Pfaffian orientation. If a graph has such an orientation, you say it's a Pfaffian graph. Okay. Of course, again, we know already by Valence theorem, unless p is equal to np, that not all graphs are going to be Pfaffians. And indeed, the simplest example is the bipartite graph with 3 and 3 vertices. So K3, 3 is not Pfaffian. So this graph here is not Pfaffian. That's an exercise. Exercise. Which one? Exercise 2. And actually, so maybe a little digression here. It's basically the only one in the meaning. So there's a theorem. So actually, it is. I'm going to put the only one. The following sense, it's a theorem by Little. So fact, this is due to Little in 1975, that a graph is Pfaffian if and only if it does not admit K33 as a, and here I'm not going to precise, the terminology is matching minor. I mean, so I'm not going to be precise here, but you get the idea. So basically, well, that's the only obstruction basically to being Pfaffian. So the question now is, can we find a big class of Pfaffian graphs? Okay. And that's the subject of the next section, Castelline's theorem. Again, note that until here, I'm still doing combinatorics. I'm still having an abstract graph. I never embedded my graph in anything. Okay? And now we'll start to embed graphs. So assume that G is planar. Okay, now we start. Now we have graphs that are embedded, no longer abstract graphs. Then any, okay, so some terminology, then the connected components, of the plane minus the graph are called faces. Faces of G. Okay, note that if we orient the plane, can give an orientation of the plane. Let's say we're going to picture this orientation as counterclockwise. Counterclockwise. This induces an orientation on each of the faces, and therefore an orientation on their boundaries as well. Okay? This induces an orientation of each face, F, and hence of their boundary, dF. And we will always, we'll just picture it all the time counterclockwise. So if we have a face, we'll always orient the boundary counterclockwise like this. Okay? This is just a convention. You could do the whole trick with doing everything clockwise. It's completely fine. But you just need to fix one orientation of the plane once and for all. Okay, so it means that if you have a fixed orientation of the boundary of each face, it makes sense to count, when you have an orientation, it makes sense to count the number of edges where you're this n omega, okay? Hence, for each omega as before, we can define n omega of the boundary of F. Before, we're only looking at n omega of an even cycle. In this case, there's no problem because you can orient it any way you want, and you will always have the same parity for this. Now, of course, a face might might have an odd number of edges, like this one, for example. And in this case, the parity of this number will depend on the way you orient your face. But here, we just fix one orientation, and we'll always go this way. Okay? Therefore, it makes sense to define this thing here. And the trick of Castelline is to say, OK, how can I want this n omega to be odd each time I have a cycle that is blah, blah, blah. Okay. Well, you have a cycle. It's a simple closed curve in the plane. Well, a simple closed curve in the plane, it bounds faces. And what we're going to do is we will ask that this is odd for each face. And the thing is, it will work. Asking simply that this is odd for each face will ensure that the orientation is actually Pfaffian. This is what we're going to prove now. And here you see already where it's going to be really complicated if it's not planar, right? If it's not planar, you have a cycle on the torus, I don't know, it's not bounding faces a priori, so you cannot just do the same trick. But for now, we're just looking at planar graphs, so it's completely fine. It's actually amazingly simple, this solution, but it's very, very nice and powerful. So here's the theorem. It's due to Castelline. There are other authors, such as Temperley, Fischer, but I'm going to just quote Castelline. So sorry, other people obtained this independently. They're not co-authors. It was in 61. So for given any planar graph, G, there exists an orientation omega such that n omega of the boundary of each face is odd for each face F. Furthermore, such an orientation can be constructed. Such an orientation can be constructed in polynomial time and is Pfaffian. I immediately state the corollary. For planar graphs, you can compute the partition function of the Dimer model in polynomial time. Okay. Okay, you can find the right orientation in polynomial time, and then you just compute a Pfaffian, and you're done. You take an absolute value at the end. Okay, so I hope I'm going to be able to prove the theorem. Yeah, I think it's going to be okay. And now I'm going to follow almost. So Castelline published several papers. In the first one, he was only considering the square lattice, and then he considered general planar graphs. So this is a version that he published in 66. It's just 3 lemmatas that are very, very easy. So really, I'm now almost following exactly what Castelline did in a subsequent paper, not in 61. So the theorem follows from 3 lemmata. Lemma A. First lemma is about constructing the right orientation. So given G planar, one can construct omega such that n omega boundary of F is odd for every F in polynomial time. And maybe just a terminology or a remark. So Castelline, he called this an admissible orientation. We will call this a Castelline orientation. Now people call this a Castelline orientation. So this is called a Castelline orientation. The proof is extremely easy, so I'm going to give you some kind of an algorithm that I will illustrate with a stupid example, okay? So as an example, I will take this graph. So step 1. Consider the dual graph G star and take a spanning tree T in this dual graph rooted at the outer face. So, example here. The dual graph, what is it? So I think you know about this. So I take one vertex in each of the faces, including the outer face. And then each time I have two faces that are adjacent, I put one edge. I'm not going to draw the entire dual graph because it's going to be a mess because this outer face is linked to too many. But I will directly take a spanning tree, okay? So let's take, for example, this. Okay, this would work, right?
What do you mean by rooted? Every edge?
Yeah, okay, so I just mean, it doesn't mean anything for now. I mean, it's going to be in step 3 that it makes sense. Here, you just put some roots here. It means here, this one, you're not going to move. Okay, this one is stable. Just mean you just remember this one is special. Okay. Step 2. You orient, so remember, the aim is to orient the edges of G. So you orient all the edges of G that are disjoint from T in an arbitrary way. Okay? Orient the edges of G disjoint from T arbitrarily. So I will continue everything on this drawing. I hope it's okay when you take notes. So okay, I just pick anything here. And I have this one. Right? Step 3, and this is where the root comes in. Now you really look at this as a tree that is rooted here, and you see that you have leaves. And now you will do what in English is called pruning the tree. It means you just remove the leaves one after the other. And so, prune, is it this way? Maybe, I'm not sure of the spelling, it's okay. Prune the tree. i.e., remove the leaves one by one until the root, until, well, not until the root, but maybe until the trunk, right? So the last one is like the trunk. Let's say until the root. And at each step, what happens? At each step, you need to orient one more edge. But at each step, you have a single way to orient it so that it works. So let's look at this one. So here, I want to remove this one here. So I want that when I go around here, I have an odd number of edges that do not go in the right direction. And here, I go in the right one, in the right one, in the wrong one. So the last one, I need to go in this way, right? If I want this face to be oriented with the condition, I need to orient it this way. So I will not draw any more things on this drawing, but until the root, at each step, it determines an orientation of the corresponding edge, primal edge, right? Not dual edge, but primal edge, so that the corresponding face, the face corresponding to the leaf that you're pruning, corresponding face, is oriented the way we want. Is oriented with an omega of the f odd. Okay, so maybe I will do this with another color. So here, as I said, here you would need to go in this direction. Okay. Let's do this one as well. Here they all go in the right one, so I need to go in the wrong one to have something odd. And then I continue. You see my tree now is moving down. I go to this one. So right, wrong, so I need to be right here. Then I move to this one. Wrong, right, right. So it means I need to be right. Okay. Then I move to this one. Okay, okay, not okay, so I need to be okay here. And the last one, not okay, not okay, okay, so I need to be not okay. This way. Okay? I don't know if I hope you can see the colors. And that's it. Okay? That's the end of the proof. And it's an algorithm. You can do it efficiently. Note that this could still have been worked out if the graph was not planar but embedded in the surface. Okay, we're going to come back to this. But here you don't really use the planarity. You just use the fact that the graph is embedded in a surface. But any finite graph can be embedded in a surface. So, okay, this can be worked out. Second lemma. Now it's really, here we will really use the planarity, not embedded in any surface but in the plane. Okay, let G embedded in the plane, and omega a Castellan orientation. Then, so for any even cycle, any cycle of even length, I'm going to say even simple closed curve. To be sure we're at the same page for terminology. So really a simple closed curve, C in G, oriented counterclockwise. So G in R, omega, a Castellan orientation for any, let G, so B, Castellan orientation, okay. Then for any even simple closed curve C in G oriented counterclockwise, actually I don't need to be even. For any simple closed curve oriented counterclockwise, so imagine you have a huge curve that is oriented like this, that is in G. We have that n omega of C plus the number of vertices of G enclosed by C, this is always odd. Okay, so here you have your cycle. You might have some number of vertices. You look at the number of edges that are oriented in the wrong direction when you go around the cycle counterclockwise. You add up the vertices inside. This is always odd. Proof. Okay, and here now we're really going to use planarity. So since G is in the plane, since G is planar, C encloses a number of faces. Is the boundary, let's put it this way, is the boundary of, let's say, k faces. K greater or equal to 1 faces of G. Right? And now what we will do, we'll make an induction on the number of faces. So we will make an induction on this number of faces. Okay, k equal 1. K equal 1, well, this is exactly the definition of a Castellan orientation. K equal 1 means if you have a simple closed curve oriented counterclockwise which bounds a single face, well, that's the boundary of a face, then n omega of C is odd. Because of course, inside a face you have no vertices. Okay. So this is okay by definition of a Castellan orientation. Well, by Castellan's condition, so a Castellan orientation. Let's make the induction step. So let C be a simple closed curve bounding, say, k plus 1 faces. So I will make a drawing here. So now I will pick one face inside. So pick one face F inside C such that F meets C along an interval. Okay, so let's do it. I don't know, let's say that we have a face like that, for example. Okay, so this is C. Okay, my curve bounds k plus 1 faces and encloses and enclosing, let's say, m vertices. Now I pick a face inside C. It looks like this. You can always find such a face. That's not completely true. You have some degenerate cases, but you can work them out as well. It's fine. Okay, and now I will look at C prime, which will be this, okay? So this defines, this defines a new simple closed curve C prime, okay? C prime, which encloses k faces, right? It encloses one less face than C. Okay, I need one more notation. It's going to be the number of edges that C and C prime, the number of purple edges here. So let's say that here, number of purple edges, let's say this is L. Okay. So note that since C encloses m vertices, C prime encloses m minus L minus 1 vertices, right? You have L minus 1 vertices that are not enclosed. That is m minus L plus 1 vertices. By induction, we have that n omega of C prime plus the number of vertices enclosed by C prime, that is plus m minus L plus 1, is odd. Okay. Now we are almost done. Finally. So what we really want to compute is n omega of C. Okay. So n omega of C, I need to count the number of edges that are not oriented the right way when I go around C counterclockwise. What I can do to compute this, I can do the following. I can compute everything along C prime, plus compute everything along the boundary of F. And then if I do this, I will have counted one too many for each of these edges, because each of these edges will contribute exactly 1 to this double sum, right? The side where it's counted in the wrong direction. So what I get is n omega of C is equal to n omega of C prime plus n omega of boundary of F plus L, or minus L. I mean, I'm computing modulo 2. Okay, so let's say minus L. Okay, now this is okay, so it means, so now this thing here means that this is congruent to n minus L, this first term here. And then here by the Castelline, so here I use induction, or let's say this thing here, plus the Castelline condition, m minus L plus, so this must be odd, right? Minus L, so this is congruent to m plus 1 modulo 2. So it means that n omega of C plus m is odd. And this is what we're trying to prove. I just keep this lemma because it's, now I'm almost done. Third lemma. A Castelline orientation is Pfaffian. And you agree that if we prove this, we're done, right? We'll have constructed an orientation such that everything works. Proof. So let omega be a Castellan orientation. And what do we need to prove? So remember, for an orientation to be Pfaffian, you need that whenever you have a cycle of even length such that when you remove it, you still have a perfect matching. This one has an omega which is odd, right? So let C in G be an even cycle such that you have a perfect matching when you remove C. Well, now let's think a little bit. You have your cycle in the plane. When you remove it, it has a perfect matching. It means that the number of vertices inside C is even, since they can be matched, right? A vertex inside C cannot be matched to a vertex outside C. Again, we're in the plane. So such a cycle needs to enclose an even number of vertices. So such a cycle encloses an even number of vertices since they can be matched. Right? But this means that this is even, this means that this is odd, and this is what we were trying to prove. So by lemma B, n omega of C is odd, so the orientation is Pfaffian. Nice, huh? It's almost too simple, but this result is really the cornerstone of the study of the Dimer model. Maybe I'll just finish the class with an example, like a didactic example, to be sure that we all agree on the definitions. So again, this example is going to be didactic. You will have some other examples in the homework. Again, in these examples, we're just checking that it works. I'm not claiming that this is the best way to compute the Dimer partition function in these examples. They are too simple. But next week, we're going to see that we can actually compute the number of perfect matchings on a square grid, n times m. And this is really not trivial. So you will see. Then you will have a Pfaffian of a big matrix. You can diagonalize this matrix, and it's quite amazing. So this example is less amazing, but let's do it anyway. So I'm going to take an example that is actually not simple. OK, I number the vertices 1, 2, 3, 4, and I put some weights, nu1, nu2, nu3, nu4, nu5. OK, that's my weighted graph. OK, I need to find a Castellan orientation here. So here I'm going to orient both in the same direction. OK, because now if we go along here, it's indeed odd. And let me pick the same orientation as on my notes. So here, orient like this, and like that. And we check indeed. If we go along here, agrees, agrees, disagrees, it's fine, it's odd. OK? And so now, let's compute the actual matrix. A omega is what? So it's a 4 by 4 matrix. OK. I'm not going to write this part. So 1, 2. So going from 1 to 2, There are two ways, so what I have is plus nu1 plus nu2, okay? 1 to 3, nothing, 1 to 4, nothing. 2 to 3, I have minus nu3. 2 to 4, plus nu5. And 3 to 4, plus nu4. And here I have the skew symmetric correspondence. And so this is really a didactic example because you remember the formula we had. So it had three terms. The first term was this guy multiplied by this guy. So that's nu1 plus nu2 times nu4. And then actually the other terms were involving this term and this term, so we have plus 0, plus 0. So what we get is nu1, nu4 plus nu2, nu4. And indeed, this of course is the partition function for the Dimer model in this graph, because this one here corresponds to a Dimer configuration like this. And the second term corresponds to this one. Again, I'm not claiming that it's such an achievement to make this computation. You will have other examples in the homeworks where it's really just doing reality checks, right? So it's examples where the partition function is obvious, but it's kind of nice to see how the orientation gives you the right sign. It's a little bit more interesting than this example. And so other examples in homeworks. And okay, so next time we'll make some more interesting examples, and then we will see some consequences of the theorem that you can compute some other interesting quantities related to the model, like edge-edge correlations. You will get them immediately. That's where we're going to use the properties 5 and 6 of the Pfaffian. And then I'll ask the question, what about general graphs that are not planar? What can you do? And well, a general finite graph can be embedded in a surface, a fixed genus. Part of what we did here, we can still do. We can still consider Castellan orientations, etc. But of course, the proof breaks down at lemma B, basically. It doesn't work. But there is still a way to make things work and to have a closed formula for the Dimer partition function, but this is going to take some technology. And so next time, I'm also going to start some kind of a crash course on homology theory, on spin structures, and quadratic forms. These are the tools, the geometric tools that we will need. This is going to be without proofs, and then in 2 weeks we will prove, with these tools, we'll prove a general Pfaffian formula for a graph embedded in any surface of any genus. Okay? Very good. Have a nice week. See you next week.